Okay, we're going to deal with matrices briefly. There's much more that we did in linear algebra, but let's just review this. Um, so a matrix is a rectangular array of numbers. In this text, they're using capital Roman letters, Latin letters, and they also use this kind of notation to indicate the matrix. So they do it this way, and they do it this way. And as we said earlier, the number of rows is mentioned first. So this matrix has m rows and n columns. And then also the subscripts for the individual elements. You mentioned the row and then the column. So this is in the second row. And the first column, so you put a 2 and a 1. And this is in the mth row and the second column. So the first index always represents the row and the second the column. They say if you have a vector in Rn, you can think of that as a matrix. So if you have this vector, you can think of it as a row vector or as a this is a matrix with one row. They say more typically it's usually thought of as a column vector, like this. But either way is possible. They say they don't use double indices since there's only a single row or a single column. But you could use double indices here. You just have, this would be A11, this would be A21, and AN1. Or if you did it this way, this would be A11, A12, A1N. Then they say you could also think of a matrix as a bunch of row vectors, like this. A first row vector, second row vector, with each row vector being in Rn, since there are n columns. Or you could think of it as a bunch of column vectors, and each column vector is in Rm because there are m rows. Okay, so just like with vectors, we had some operations between vectors. Now we're going to have operations between matrices like addition, scalar multiplication. They say they're really no different than the operations on vectors. So you can, if you have two matrices of the same size, then you can add them. If they're not the same size, we don't talk about adding them. And you just add the corresponding entries. And that is the entry in the ith row and jth column of the result comes from the ith row and jth column of the first matrix plus the ith row and the jth column entry of the second matrix. So in other words, where does this 8 come from? It comes from this entry plus this entry. But they have to have the same dimensions to add them. Then we can talk about properties of this addition. So it is commutative. That is, you can switch the order. Remember, we had one case where things weren't commutative, one important case, and that was the cross product was not commutative, but this is commutative. You have associativity. Remember, the cross product didn't have this property either, but this matrix addition does. We have the zero matrix, which is the matrix which, when you add it to a matrix A, gives you A back again. And that's going to, of course, be a matrix with all zeros in it. And then we have scalar multiplication, which just means if you want to multiply this matrix by 3, just means you multiply each entry by 3. So this gets multiplied by 3 to give you 3. This gets multiplied by 3 to give you 6, and so on. Then we have properties for scalar multiplication of matrices. K plus L of A, you can do this, you can do this, you can do this. So if you want to prove these, they say, we'll leave it up to you. So I'm not quite sure what she means by this. Just as defining products of vectors needs to be unexpected in order to be useful. I'm not sure what that means, but except that, when we talk about multiplying matrices, we have two ways. We have the dot product and the cross product, and in some sense they're both, I guess, sort of unexpected. But anyway, the question is, what are we going to mean by matrix multiplication? And she says, actually, it's somehow sort of related to the dot product of two vectors, in a way. So let's see what we mean by it anyway. So suppose we have a matrix A and another matrix B, and A is of size m by n, and B is of size n by p. So whenever you do matrix multiplication, if you're multiplying A times B, you have to make sure that this entry, this number here, which is the number of columns of A, has to be the same as the number of rows of B. That's part of this definition. So we write the product like, there you're writing the product like that, AB, and they say that the size will come from here and here, so it'll be an m by, so these things have to match, and then the size of the new result is going to be here and here. Anyway, let's see what this means. Maybe it's too much to say it beforehand. Okay, so anyway, we have a matrix A here and a matrix B here, and we have to have, like we said, the sizes have to there's certain restrictions. But anyway, this is a matrix A, this is a matrix B, and they sort of just mention or sort of show that, of course, you can view these as rows, you can view these as columns. Of course, you could also view these as columns, but for this situation, it's useful to view these as rows and these as columns, but you don't have to. So the question is, what is the product of this matrix and this matrix? And this gives the answer, but this is a little bit confusing. So let's look at another way of understanding it. Let's try an example. So here we have this matrix and this matrix, and we'll come back to this in a minute, but let's do it let's just look at an example first. So first of all, how many columns are there here? There's 3. And how many rows are there here? There's 3. They have to match for this to work. Okay. So and then the size of the result is going to come from not the number of columns here and the number of rows here, but the number of rows here and the number of columns here. So how many rows are there? 2. And how many columns are there? 2. So the size is going to come from that. In other words, the size is going to be 2 by 2. All right. So the way to think about this is to recognize that the result is going to be a 2 by 2, and then ask, okay, what is the first entry? What is this entry? What is this entry? And what is this entry? How do we get these entries? So they say, for example, the 2, 1 entry. Remember, we always write the row first and the column second. So 2, 1 entry means the second row, first column entry. So that's this 47. So where does this come from? So it comes from, if you want to know this entry, you say, oh, well, that's the 2, 1 entry. And then you say, okay, so that means I want to take the second row from here and the first column from here. Okay, it's a little hard to remember at first, but that's what you do. So if I do that, if I take the second row here times this column, so what do I mean by times? Now we use what she said, which is, it sort of comes from dot product. We take the dot product of these two matrices, this matrix and this matrix. So if you do the dot product, you get 4 times 0, 5 times 7, and 6 times 2. Okay, and that's what they wrote here. So that's 47. So there are other ways to sort of visualize what we just did, but I think this is one way, and you may have other ways, but I'll just say that. Okay, so how do I get, for example, this entry? So I say, well, what row and what column is that? That's in the first row and the second column. So that means you take the first row from here and the second column from here and do the dot product. So that's 1 times 1, that's 2 times 0, and that's 3 times 4. So this is how you can compute the resulting matrix. And you do have to recognize what the size of the resulting matrix is going to be in advance. And we said that comes from if you take an m by n and an n by p, the resulting size will be an m by p. Okay, so that tells you that, what's the b times a? So b times a, this is going to be a 3 by 2, and this is going to be a 2 by 3, so b times a is going to be a 3 by 3 matrix. So it's not even going to be a 2 by 2 matrix, it's going to be a 3 by 3 matrix. And so obviously, you can see right here that a times b is not the same as b times a. So it's not what we call commutative. Okay, so going back to this definition, so we said, how do we get the ijth entry in the result? So that would be like, how do we get this result? So the ijth entry, if this is the ijth entry, I would be the row, so this 2, 1, because the column is 1. So this would be the 2, 1 entry. So in general, how do we get the ijth entry? So this tells you, you take, if I want the ijth entry, then I have to take the ith row from the first times the jth column of the second. So the ith row entries, what do they look like? They all have I for their row entry. So the first entry is I, but the second entry goes 1, 2, because this is the column, up to n. And then what does the this column vector look like? The row changes, but the column is always j. So the row is, so it's 1j, 2j, nj. And now we just said you're going to take this times this, so you're going to get you're going to get ai1 b1j, ai1 b1j, plus ai2 b2j, ai2 b2j, and you keep doing that until the end, a1n bnj. Okay, so this is the answer for what is the ijth entry. So you have to do all that just for one entry. Okay, and then of course you could rewrite this more compactly like this. Really? Well, let's make sure. So what changes here? Each one of this has an I, J, and this is, we're trying to get the ijth entry. So what is changing? They all have ij like that. What's changing is the 1 here, which is also 1 here, the 2 here, which is also 2 here, and so on. So what's changing? Just that. The 1, the 2, the 3. And where are those? Those are here and here. Here and here. So where are they? Here and here. Right? So it's, you just let k go from 1 to n. Okay, so you can write it like that. Okay, so coming back to here, we saw that A times B. Sometimes this is called A cross B, so I keep saying A cross B, but A times B is not equal to B times A. On the other hand, some things do hold for matrix multiplication. For example, it is associative. A, B, C, like that, is equal to A, B, C. K, which is a constant, times AB, you can do the K times just the A first, or you can do A times KB. Okay, you do also have distributive property like this, and also like this. So the only one we don't have is this one. Okay, one more operation that we're going to define, and there's nothing like this for a number, and it's called the transpose of a matrix. So let's look at an example. So here's a matrix A. How many rows does it have? It has 2. How many columns does it have? It has 3. Okay, then we're going to define something called the transpose of A, which we'll denote like this. And you just take the first row of A, and in the transpose it just becomes the first column of A. And you take the second row of A, and in the transpose it becomes the second column of B. So it's just like kind of flipping it. Or you can say that the ijth entry of this one, so let's take this one. Where does this come from? This is what entry? This is the 2-1 entry. Right? The 2-1 entry from here comes from here. What entry is this? This is the 1 first row, second column entry, the 1-2 entry. Okay? So the 2-1 entry comes from the 1-2 entry. And what is this? What is this? 4. This is the first row, second column. The 1-2 entry, where did that come from? That came from here. What entry is this? This is the 2-1 entry. Okay, so you can see that the ijth entry of this one, of the transpose, is the jith entry of A. Now, one thing that seems pretty obvious is that if you do the transpose and you do the transpose again, you just get what you started with. If you start with A, you get A back again. On the other hand, this is something that you have to prove. I mean, this is almost completely obvious, but this one is not obvious, that AB transpose is equal to B transpose A transpose. So it doesn't look like she proves this, which is a little bit surprising, but maybe later she'll prove it. Or you can try and prove it. Or you can look it up and read a proof of it somewhere. So they say sometimes we use this kind of for notational purposes. So suppose you have 2 vectors A, B in Rn, so they're both in Rn. Then we can take the dot product of them. That's one thing we didn't mention, and that is you can't take the dot product of vectors that are in different, different dimensions. So if A is in R5 and B is in R7, you can't take the dot product. It doesn't make sense. They have to be both in Rn to take the dot product. But anyway, if A and B are in Rn, then the dot product we know, of course, is just this. But we could view that as this times this, right? Now we're talking about this as a matrix, and this as a matrix. But what is the result of this matrix times this matrix? This is a 1 by n matrix, 1 row by n columns. And this is a n rows by 1 column. So it's a 1 by n and an n by 1. So we're allowed to do it. The sizes match, the n's match. And the result is going to be a 1 by 1, which is sort of, the result is a scalar, and we're saying the result is a matrix. but the dimension of the matrix is 1 by 1. So basically, I guess they're saying that that's like the same thing as a scalar, in a sense, because it's just one entry. And if we write this like this, which we're going to do sometimes, we would say this is, it doesn't have to be this way, because we already said that A, now what they're, okay, so this is a row vector times a column vector. But usually, I guess usually we think of all vectors as column vectors. So if you had 2 column vectors, you couldn't multiply them, because we said that ends wouldn't match. So in order to do it, you have to make the column vector a row vector. So they're saying do this. That makes the, so A apparently, I guess they're assuming A was originally a column vector. They say that actually, okay. So if they're both column vectors, then you have to take the transpose before you could treat them as matrices and multiply them. A little bit. Anyway, okay. Okay, so we have a little more to do with matrices. And basically we're going to say a very interesting fact, which is we can treat matrix multiplication as a function from Rn to Rm. Now, have we talked about functions? No, we haven't talked about this yet. Okay, so this is very important, and we'll be sort of thinking in this way often.